implement high-level synthesis optimization, and we will learn how to control the synthesis result of HLS generated circuit through different synthesis options like arrays, loops, and functions. So we will go and implement the bubble sort algorithm. So I'll go and create the new project. All right, now I'm not gonna open, create a new workspace and name it bubble sort workspace. Okay. And after that I will set the project options. So with the clock period I'll go to 2000 nanoseconds, sorry, to give us the frequency of 15 megahertz. Our next part will be setting the FPGA family device. Here I'm gonna choose Cyclone V because we are using the DE1 stock FPGA board, as we can see here, and the speed grade is -6. The device name is 5ESEMA5, and the package name is FC31. Alright, and I'll go to the basic libraries and I'll ping them as well. These are the mainline libraries that we need for our design. I saved them here in the download. I'll call them, and I'll go call the functional unit library as well. So after I added all of them, right now my next step will be going and apply all the changes and create this project. So as we can see here in the dark blue folder, we have the source file here. So I'm going to import the one that we have in our design, and this is a pure C++ code, as we can see here. So our next part will be is changing it and make it synthesizable. So I go to the analysis option and make sure it's gonna be like, I will go to analyze and use the BDL parser for it. Click on OK. Alright, so I've already prepared the code here and it's ready to be synthesized. And I'll explain in a few seconds what it does. So here we have changed everything, and I make it used if-div directives. For example, integer main is not synthesizable, so to make it synthesizable I use the PDL here, and this part is synthesizable, so I don't need to use any if-div directives with it, and so on. So after I've done with the bubble sort algorithm, and here everything is synthesizable, so I didn't add anything. Let's say, for example, this code here is not synthesizable and it's assigning the input data value to the array. So to make it synthesizable, I used else statement and add this equivalent code for it for the PDL. So I'll go and analyze the code. Yes, save the change, and everything went successfully. After that, if we can see here, the bubble.if file has been generated. I will go and for the synthesis option and make sure that the automatic scheduling is adding to 1, and here I will add the generating IO timing signal, because I have here, I will go with this choice, which is valid for each port is generated as an output port. And after that I finish, I will go click OK. After that I will go to the RTL synthesize RTL code file, so that will give us the quality of report file, as we can see here, quality of results, sorry, that it has all the information about the circuit that generated for us. So it has 3,653 LUTs, and it consumed 300.301 register with a latency of 16, and the critical path delay is 20.6616 nanosecond. All right. After we're done, we can explore the results here. We can see the data path, as we can see here, for the design, and also the binary state machine in this green box here, and all the states that it has for the design. Cool. Our next part will be doing the signal tab. So this is all the signal that we have in the design, and it gave us through the 16 finite state machine that we have in the circuit, and it shows us everything. And to see also, we can see the constraint file here. If we open internally, it takes from us also only 13 to 32 loops to finish all the bubble sort things, because it's shifting the data from within the same array. All right, what else we can see here in the synthesis option? We can see the synthesis graph here as well. It shows here how many state machines that we have consumed in the Circus 16. If we want to see also the LUTs, it says like 3653 and so on. All right, so our next part will be generating the logic synthesis script code for it. So to make that, I will go and click on execute. All right, and as you can see here, it generates for us this blue circuit that has the Verilog code for the design with inputs of in data and outputs, and it generates for us clock and reset. And as we can see here, the control signals that we have them to the design by using the control signal already. All right, so I'm going to simulate the circuit and see test it in both cases for the software and for the RTL level design. So to do this, I need to do some steps. I will go and create a new scenario, and I will choose the behavioral C++ code and name it as bubble sort underscore software. All right, and go with this one. Choose this code, C++ compiler, and click on OK. For the build, I will add C. OK, and click on OK and apply. I will add the input file that we need to test the values for the design. And yeah, everything is going good. So if I go and build, it gave us some error here, which is fine because I think we don't have this file is already installed on our machine. So we will go and do this by using the terminal. So we got this error. After that, we'll go here and implement it by using the direction from the terminal. All right, so where we have saved here, simulation work, and I'm gonna take what property and take all of this. All right, so I'll go here, sorry, and I'll paste all this, list. Yeah, I'll go to the simulation work folder, that's all it contains, and it only has this one. All right, so I'm inside it, so I'll make the file. Okay, it's generated, updating, everything is good. So if I go and click list, yeah, it generates for us the bubble sort. Yes. Okay, so after we finished executing the software, we got the result here from 1 to 8. Okay, that's cool. We are going to implement right now the simulation part, and sorry, the RTL part. So I'm going to bubble sort, create a new folder. I'll call it the bubble sort underscore RTL, and I'll choose RTL and RTL only. Okay, so if I click here, RTL, so it's create for us. Right now, I'm going to pick every valid cycle because that will give us that will collect the every clock cycle from the design. And I will go here, choose decimal, yeah, and BCD file, not all of them, just the port. Click on OK. Our next step will go and taking the out data and in data from the software design and send them to the RTO and change their extension to TLV. All right, and this one to TLV. Okay, so I think we are all set with this. I'm going to build the design and then click on simulation. So it's going to do it for us. And after that, if I go to the pattern, it's create for us the TLV file that has sort the input data. This is the input data, and it sort them using bubble sort algorithm from 1 to 8. All right. So our next step is to evaluate the circuit and try to optimize it by using Pragmas. So I'm going to add here, to add a Pragma here, I'll go to right click on it and attribute and choose array value. So I will pick it based on the circuit that we have here. So for our part, the professor wants from us to calculate it as, if we go here, RAM and unroll for the loops and unroll for the loops. Okay, I'll choose RAM and I'll click on insert it. So as you can see here, it adds a pragma for it here. All right, and for the function, for the first function here, I'm gonna add another pragma. For the loops, I'm gonna choose not folding, as we can see here, unroll times, and value will be as you want from us, all. Okay, so all insert. We added the pragma, the first pragma here, and I'll copy and paste it here. After that, I will save the design and I will reanalyze everything, go here and regenerate the design. And right now as we can see here, the RTL has been changed, and as you can see here, the number of latency were increased and the number of pins were increased as well, but however it reduced the number of LUTs and the number of registers. So if we can see here, if we can compare it with the first design without any pragmas on it, if we go back in the result, we can see here like it was 3000 and right now it is 1000. So this is good in terms of the area, but it's not good at all in terms of latency, and it reduces as well the critical path for the design, because here it was like 20 seconds and now we have it like 9 nanoseconds. Okay, so let's do the other part for the design and change, trying to manipulate with the pragmas themselves. All right, I'm gonna change it and put it as register all 0. So I will put them as register. I'll change here. I'll change the pragma for the array as register, and here the pragma will be all, and here I'm gonna put it like 0 and see what does it change. Control S, I saved it. I'm going to just recompile the design, parsing the design. Okay, it's done. And after that, I will resynthesize the design. And then I will click on simulation to see the output data that will give us. Okay, that's good. So as we can see here, it reduces the LUTs to the minimum, as we can see here, and that will help us, but the latency were increased and the critical path were increased as well, which is good. So our last thing is I'm going to put all of this as all, That means we will unroll all the for loops in the design, like it design them, and everyone will make like 8 for loops sequentially. So I'm going to say, click on save, analyze the design, regenerate. Yeah, and it give us a come back again like it was like the first thing without adding any pragma. So we are having the same results here. That means if we don't have any pragma in the design, it will unroll by default all of them, and it will unroll all of these here, and it will deal with the array as registers. And we can optimize the design using any other stuff like decreasing the number of in terms of data width, that data bit that we have here in the design, and that will help us to reduce the number of uh, the circuit. So if we simulate the circuit here again here, we will get the same result but with different hardware implementation. So to do so, we can also here changing the synthesis option. So if we go to the clock or reset, we can play with all the macros here, with all the detail. Like for our circuit specification, I choose the second one so we can have the result, the RAM, data bit width if you want to play with it, the finite state machine, or also with the pipelining for the clock circuit if we want to use the function stall port or create like component circuit. And thank you so much for watching.